So this is the start of lecture 4, chapter 4, and we're looking at chemical reactions in this chapter. So I always like to start this particular lecture talking about what makes a chemical reaction take place, to kind of introduce you to a couple of the big themes or big topics, big ideas that we're going to be talking about throughout this year. So first off, if products are a lower energy, usually you will have a going to product situation. So exothermic reactions, if you remember, delta H is called enthalpy, and we will be talking about that in the next chapter. Exothermics tend to lose energy once the product is formed, the difference. And so we have a negative there because we are saying we are losing it to the surroundings. If I produce a gas product in a chemical reaction, that's usually a favorable thing for it to happen, because what you have is an increase in entropy, or what we call disorder. The symbol we're going to see is letter S for entropy. We'll mention it a couple times first semester, but we're really going to focus on it more second semester, but I like to introduce it as soon as possible. So here I have the production of a gas from a solid and an aqueous system. So I have more disorder because of that, also because I have three things on the right-hand side. So anytime you are producing a gas, that's going to be something that does go to product. And then number 3, the production of a weakly dissociated species. So insoluble compounds, and I'll talk about that here in a second in terms of solubility rules, but what it means is if something is insoluble, it makes a precipitate. So the symbol we're going to use is PPT for precipitate. So here I have an aqueous, I'm bubbling through carbon dioxide, and I make a precipitate, I make calcium carbonate. So anytime that it forms a precipitate, something insoluble, you will make product, it will go to product. And then this last one on this page, the forming of what we call complex ions. Copper 2+ plus 4 ammonias makes this complex ion. So it's not a normal ionic compound. It has a +2 charge because of the copper, because ammonia has no charge. It is aqueous. Most complex ions are aqueous. It is a system for where you can remove certain ions by binding it with something else. But we're not going to have a huge focus on the AP test about complex ions, but we are going to see it a couple places in different labs. So that's why I want to show it to you as soon as I can. All right, so to the next page. We are talking about 3 major types of reactions, okay? So when we talked first time around, or first year chemistry, we kind of did 5 different types of chemical reactions, if you remember any of those. We break it really down into 3 things: precipitation reaction, acid-base reaction, and something called oxidation reduction, which I'm going to spend a lot of time on. So precipitation reactions was what we call your first year double replacement, where you were making a precipitate by essentially changing partners in terms of cations and anions. Acid-base is what we call neutralization reactions. And neutralization reactions was when we were talking about, doing a titration or something like that. H+ plus OH minus making water is a famous, what we call Net Ionic Equation that we have for acid-base chemistry. So these are called neutralization or acid-base types of reactions. But the last one is called oxidation reduction. It is abbreviated redox, R-E-D for reduction, O-X for oxidation. It is the movement of electrons. And we're going to talk about redox reactions specifically in this chapter. So combination reaction, decomposition reaction, displacement single and double are all considered oxidation reductions. So really, unfortunately for first year chemistry, we don't really do much with oxidation reduction that first year, but we're going to spend a lot more time this year talking about it. So precipitation reactions have to do with what makes a precipitate, what doesn't. So I gave you a solubility table in your summer packet. And so now you're going to have to be able to focus on how you're going to use this or what I'm expecting you to do. So this is a great resource to say, okay, if I have a double replacement reaction, which are going to make the solid, which are not. So please on the top write down soluble means no precipitate, while not soluble means precipitate. Okay, so any place you see not soluble, that means you are making a precipitate. And you are reading from left to right on this. It is the easiest one I could get you to use properly. So there are other ones out there, but I think this is the easiest one. So I want you to memorize the first 5, okay, the first 5 rules. So any anion attached to an alkaline ion, so that's anything from group 1, will always be soluble, If you have an anion attached to the ammonium ion, it will also be soluble. Nitrates are always soluble. Acetates, except for silver, acetates are going to be soluble. And then this last group, these are the halogens, the chlorine, bromine, iodine, other than fluorine. Keep in mind that as you go across, okay, the silver, lead 2, mercury 1, and copper 1 are going to make a precipitate. But anything else attached, say copper 2 or even lead 4, or any other cation, it will be soluble. It will be an aqueous system. So these are the 5 that I expect you to memorize and use for this class. The rest of it I will provide to you. I will block out the first 5 and you will then have the rest of it. This activity series we'll talk about a little bit later on, but that's the solubility table that you're going to be using. So solubility rules, again, you must memorize number 1 through 5. Okay, number 1 through 5. So write out an example of a precipitation reaction. We have aqueous barium chloride reacts with aqueous sodium sulfate to produce. So again, you're going to have to use a solubility table to do this type of problem. And I'm going to ask you to write 3 different kinds of equation, 3 different kinds of equation. So the first one I call a molecular equation, or your traditional balanced chemical equation. What I want is proper formulas, and then to make sure that everything is properly balanced. So barium chloride plus sodium sulfate, and it told you they were both aqueous. So the barium gets together with the sulfate, and that happens to be something that makes a precipitate. So if we go to sulfate and we read across, barium is not soluble. So that's going to be a solid, okay? And then sodium chloride, because again, sodium is an alkali metal, it will always be aqueous, it will always be aqueous. And chlorine, again, you could look at the rule. The next thing I'm going to ask you to do is to write what we call a complete ionic equation. So what you're doing is anything that is aqueous, okay, anything that is aqueous, you're going to break it up because that is what's floating around in there. So underneath each one of these, you could write aqueous next to each one, or you could just put a little arrow here and write aqueous for all of those ions, okay? What happens is once they are all mixed together, the barium finds the sulfate and starts to precipitate out, and then the sodium and the chloride ions are still in the system, still in the solution. And again, those 2 please mark as aqueous, please mark as aqueous. So finally, you have something called the net ionic equation. Now, this is the most important equation for chemists because this really tells us what is the net result, why are we doing this reaction, or what really will we see in the beaker. If I don't make a precipitate, you wouldn't see anything happening. You would just mix 2 liquids together and nothing would happen. But since you're seeing a precipitate form, that's the most important thing in this equation. So I'm going to take a look at my complete ionic and see if I have anything the same on both sides. So I see that I have sodium ions on both sides. They're both 2 sodium ions, and I have both 2 chloride ions. These are what we call spectator ions. Okay, spectator ions, and that is something, those are ions that don't get involved in the chemical reaction, but they are in the beaker themselves. The net ionic equation is then going to be anything else that is left over, or what makes a solid, or in some cases a gas, and so on and so forth. So barium plus the sulfate, and again, both of these are aqueous. So you could put that underneath or right next to them. Makes the barium sulfate in a solid. Makes the barium sulfate in a solid. Okay, so that's the basics of a precipitation reaction.